most recent edited lecture schedule is, well, they're more guidelines than actual rules, so we're probably not going to get to chapter 24 at all. Honestly, when Dr. Smithard teaches this, he only does like a single day on chapter 23 amines anyway. So if I just cut out chapter 24 that he doesn't cover anyway, I just think it's cool. And we don't do the biochem stuff because, you know, it's fine. If you need biochem, you'll take biochem. And they'll draw funny shapes, and it won't be the same, but it's fine. And if we cut out that, I think we're going to get through chapter 22 just fine. Yes?
If you have any biochem material, could you post it at least?
Yeah, absolutely. I didn't teach it last year, so I basically have what the book gave me, but I can definitely, like, give you guys the slide decks for that and stuff. And if you, do you guys like lose access to this book at the end of the semester?
We have like a year.
Yeah, it's basically December 31st of 2024.
Weird. I don't like that. I don't know, I mean.
You'd think if you purchase a book, you purchase a book, but.
Right, like, I don't know, I mean, I guess not everybody's gonna go do a PhD in chemistry, so you're all probably not necessarily gonna keep them all on your shelves forever and finally be vindicated that one time when you're like, I actually needed to go back to my undergrad book and relearn this from there, and so I kept it for a reason. It was very exciting when I realized I kept that for a reason, or I could justify it. But yeah, I guess that's not everybody. I don't know, still. I have a lot of pre-meds in here. Weird. Well, you should be able to find a PDF of the book with some of the methods that I talked about. And if you need a refresher of those methods that you should definitely not use, I will remind you in office hours of the very specific ways you should not go about trying to pirate textbooks, and also journal articles. So, yesterday, we talked about esters and amides, and I think this slide is deceptively named because reactions with ammonia and amines, esters and amides, and we get ester. Cool, ester goes ahead and does like a flip-flop switch, and instead of an ester, now we have an attack, and we end up with an amide. And then we kick off an ethanol. Yeah? Amides don't do this. So basically, if we have an ester, we can turn one ester into another ester, and we call that transesterification, right? We can turn an ester into an amide, but we can't do transamidification, which I'm making up how to pronounce because it's not a thing, because it's not a thing we can do. So if you have an amide, you're not going to be able to just react it with an amine or ammonia. So you're going to have to, where's that table? So you're going to have to take it probably here and then go up like to here or up to here and then go back down to get to a different amide, if that's what you're trying to do, right? Even when we do this with esters though, an amine, turning an ester and an amine into an amide, we're going to have to heat that and or use high concentrations of the amine. So, I mean, we're already usually using high concentrations of whatever our nucleophile is because, I mean, unless, well, if we're starting with an ester, right, because, well, if we're doing an ester to another ester, then that's equilibrium, and if we're doing carboxylic acid to ester, that can hit an equilibrium, so usually we're already doing that anyway to push equilibrium, but for this one, to even make that really go at all, you're gonna need high concentrations and probably also heating. Let's see. if you have an acid chloride. So back over to acid chlorides, the very top one that doesn't usually need help to react, just sort of does stuff, because it wants to stop being what it is. If you react an acid chloride with a salt of a carboxylic acid, you will get your acid anhydride. So that's how you make these acid anhydrides. You can't take a carboxylic acid, you have to take the deprotonated salt of a carboxylic acid with your acetyl chloride or your acid chloride, and then you're just going to kick off NaCl in this specific case. Yeah. So it's kind of like, I mean, so, you know, putting this together is, taking it apart is like hydrating it. Putting it together isn't exactly dehydrating it because, well, we had to take out the OH and the H in other ways first before we actually do the reaction, right? But like, in essence, this could have started as a carboxylic acid that you then did as chlorinated with SOCl2, right? And then this, well, you just deprotonated carboxylic acid. So it's sort of made out of two carboxylic acids, right? Yeah. This is a really useful synthesis for mixed anhydrides because, well, you have two different, like, you're not doing carboxylic acid and carboxylic acid, or like, you don't have two of the same things, you've got different functional groups, so the acid chloride isn't gonna be able to like basically dimerize with an acid chloride, right? So those aren't gonna react with themselves, and those aren't gonna react with themselves. So this can actually give you mixed anhydrides that are asymmetrical. So here's my favorite chart again. Basically, anytime you want to turn something into something else, see if it's downhill. If it's downhill, you can do it. If it's not downhill, go all the way downhill and go around. And that's kind of how you would end up doing it. Okay, reaction with Grignard reagents. So far, Grignard reagents and Gilman reagents have been real similar. I mean, Gilman reagents could couple with halogenated alkanes, right? And Grignard reagents could sometimes do that if you stick a copper salt in there, just to like co-catalyze it, right? So they've been fairly interchangeable. Not anymore. So, Grignard reagents. Grignard reagents, if you treat, so here's an example of formic acid with 2 moles of Grignard reagents, you're going to get an alcohol. So it's going to substitute twice. Now, yes, I know it says if you treat it with 2 moles of reagents, and you go, well, what if I treat it with 1 mole of reagents? Well, then you get a hot mess that is not going to be fun coming out of your column, because Grignard reagents, like, so Grignard reagents are basically, this is an irreversible nucleophile, right? It's a carbon nucleophile. So it's, in quotes, kind of like a negatively charged carbon, right? A carbanion. So once this guy attacks something, once it like makes a bond, it's not going backwards. Like, it's there. So whatever it attacks first, that's where it is forever, and that's that. Which means that you would end up with a whole mixture of, if you didn't have enough Grignard reagent, a whole mixture of some that are disubstituted, some that are only substituted once, some that are not substituted at all, and God, that would be a pain to get out of the column. You could get, no, it'd be a pain. That'd be really annoying. So, Grignard reaction, you're not going to be able to just take an ester and take off the ester part and just make it an aldehyde. You're going to start with an ester, and you're going to go all the way to an alcohol, so it's reducing it, right? did I call this one a, oh no, it's just a secondary alcohol versus a tertiary alcohol. That doesn't deserve 2 slides. But yeah, if you've got formic acid, you get secondary alcohol. Either way, you get carbon RR from this guy, R prime this way. So R prime can be, you know, carbon stuff, or it can just be the hydrogen from the last slide, and then you get an alcohol. And these two are going to be the same, right? Because I mean, the only way to try to make that different is if you just throw in a mixture of Grignard reagents, and that would again get you to a huge mess. Yes?
Where does the CH3OH come from?
So this is your leaving group, OCH3. So once you attack this guy,
Gotcha.
you're going to kick that up, and then you're going to kick this down and kick the OCH3 off, and it's going to eventually protonate itself. Oh, it'll eventually get protonated because you have to do an acid workup anyway. So, we're gonna start talking about some of the mechanisms that we care slightly less about, including, mechanisms of, because like most of the mechanisms today, most of the mechanisms are the same anyway, right? Like, kind of, because really this is the first part of this is every other nucleophilic attack we've ever seen of an ester. Because we do a nucleophilic attack, we kick up the pi bond up into the lone pairs, get rid of the MGX, who cares about that? We've got a negative charge, and I don't care what it's attached to. Because whatever it's attached to, it's not a real bond. It's only it's an inorganic people. They might call it a bond or complexation or whatever. It's not a real bond. It's not covalent. We don't care. Then we're going to kick that back down because we've got 2 CO single bonds. So we kick that back down, kick that off, and we've got get rid of this again, and you've just got a deprotonated alcohol. That deprotonated alcohol is not going to find anything to protonate itself with until your workup. And we know that because we know that in order to do this reaction in the first place with a Grignard reagent, there's no water around, right? And, well, if there were alcohols around, it would kill our Grignard reagent. So there's no protons anymore. There's no protons more acidic than this, this guy, right? Like, this guy is not basic enough to steal any protons. Because if he were, this would have stolen them first, and we'd just kill our Grignard reagent. So this guy stays the way it is. We have a ketone, and that's in the middle, but we cannot get this ketone by itself, because you're not going to be able to make, because this is kinetically controlled, because once there's an attack, like once the molecules just ram into each other in the right orientation, a bond forms and we can't go backwards, right? So there's no such thing as equilibrium when we don't have reversibility. So some of them are going to be on this step, some of them will be on this step, and some of them will still be over here. And you're not going to get your ketone by itself. Yes?
Would step 2 be reversible at all? Would that go minus, the H3CO minus, would that like occasionally attack back to the...
Yeah, you could do that. As long as you caught it before the next Grignard showed up. Yep. Good call. I don't like that they're not. Yeah. So this guy is also reversible, step 4. Proton exchanges are always reversible and basically always kicking off, reforming a double bond and kicking off a good leaving group is going to be somewhat reversible. So then we just attack again, move that back up, and then, well, there's nothing else to kick off because all of those guys have a pKa, or they would have a pKa of like 50. So bad leaving group, terrible leaving group. No way you're going to kick that stuff off. So you just protonate, well, you just leave it the way it is, and then you work it up, so that you end up protonating that, and then you'll protonate the leftover alcohol over here while you do that. So you're gonna have to put in at least twice as much acid, at least 2 moles of acid, 2 molar equivalents. There we go. If I say 2 molar equivalents, that just means, like, if I say 2 moles of acid, then I'm kind of specifying that we started with 1 mole, right? But if I say 2 molar equivalents, it doesn't matter how much we started with. It could be like 100 millimoles, but like just 2 times whatever we started with, right? Molar equivalents, is that useful? Okay, yes, did you have a, no, okay, sorry, you have a question face. Okay, so, organolithium compounds. All right, fine. These are more aggressive than Grignard reagents, so they do the exact same thing. Usually they're gonna give you higher yields. There's no reason to use this unless for some reason your Grignard reagent doesn't work because, I mean, it's lithium, let's just not. Gilman reagents. Gilman reagents are finally not the same as, or pretty much the same as, Grignard reagents. So, in this case, you can take an acid chloride, so we're not reacting it with the same thing, right? A Grignard reagent could totally react with an acid chloride. If it can react with, let me go back to our, this. That. So, Grignard reagent can attack here. It's going to be able to attack that, or wait, here. Grignard reagent was able to attack here. It's going to be able to attack any of these. Like, just anything more reactive. But with Gilman reagents, we can do something special. So if we only use an acid chloride, which yes is more reactive, but we take the whole reaction and we cool it down to -78 Celsius. So that is dry ice and acetone bath. That's the temperature of a dry ice and acetone bath, which hurts. Like, nitrile gloves do not, it hurts. It is physically painful to touch things coming in and out of the bath on that. Ask me how I know. And glass gets very, hot glassware looks like cold glassware, and very cold glassware kind of feels like hot glassware sometimes. But anyway, if you cool this down in a dry ice and acetone bath, and do this reaction in ether with a Gilman reagent, you can actually get 1 equivalent of Gilman reagent. Well, you can get 1 substitution of this, which I guess technically Gilman reagents are 2 alkyl groups per carbon, so I guess technically we're using 2 molar equivalents of our acid chloride and 1 molar equivalent of our Gilman reagent to end up with 1 substitution for all of them, right? So this one stops here if you cool it down that much. So yay, we can finally do something with Gilman reagents that's like significantly different. The tetrahedral carbonyl addition intermediate is stable, so under those conditions, this chlorine not getting kicked off, just having the oxygen here and your methyl group here and just the chlorine on there too, at this temperature, under these conditions, that's actually stable and you don't kick off the chlorine. So that's why it doesn't progress any further. If you ended up kicking off the chlorine, you would make your nice electrophile again, right? And then you'd be able to attack again. But in this case, the reason that that it doesn't attack twice is because we cool it down enough that that tetrahedral intermediate is stable. So it just lives like that until you, I guess, neutralize the rest of the Gilman reagent and then warm it back up. They're only going to react with very reactive acid chlorides, though. So Gilman reagents, we're not going to use them with anything else. Only acid chlorides, not aldehydes, ketones, acid anhydrides, esters, amides, nitriles, none of that shit. So that's a thing young reagents also do differently. Reduction of esters. Good to move on from carbon nucleophiles. All right, reduction of esters. One of your homework questions is a reduction mechanism, and your homework is on completion anyway, so like, I don't know, try it, but also we're not going through the reduction mechanisms. We're not drawing them out completely, and I'm not gonna make you know them because they're not super different. Like, they're still basically the nucleophilic acyl substitution that we've been doing for like everything else. And honestly, I see no reason to not just call your nucleophiles red. H minus. So, if knowing the mechanism kind of helps you be able to predict products so that you don't have to memorize reactions but can like figure out reactions or figure out products, then treat all of these reducing agents as H minus, just hydride, and whatever stuff around it necessary to make that hydride, well, able to exist as a hydride. And then you're gonna have to remember their different strengths and different things they're able to do. So, if we use LAH on an ester, we're going to break this, right? Because, well, the first time we attack, we always end up kicking off this part of the ester that goes and becomes an alcohol eventually. And then, well, LAH is also going to reduce an aldehyde or a ketone, so it's just gonna keep going, and you're gonna get an ester reduced all the way down to 2 alcohols. Split right there. Sodium borohydride. Esters, technically, if you have, I don't actually know how long this takes, so I'm gonna be either surprisingly literal or probably a little dramatic. Millennia. If you have like millennia to do this, then you can hang around long enough for sodium borohydride to reduce an ester. And that would just be the first step of reduction. But like, it's not gonna happen. It just doesn't, it's so slow, it's not even worth mentioning that it happens at all. So actually, sodium borohydride ends up being really useful for selectively reducing aldehydes and ketones when there's an ester nearby, because it'll pretty much leave the ester alone, and it'll go ahead and reduce aldehyde or ketone down to one step, or down to an alcohol. So that's cool. We started with the really aggressive one, LAH, and if we put that with an ester, breaks it and reduces it all the way down to 2 alcohols. And if we put sodium borohydride, less aggressive, it doesn't even do anything. So is there a way to turn an ester into to reduce an ester into a ketone or aldehyde? Well, I guess just aldehyde. Yeah, just into an aldehyde. There is. It's this guy. It's called Dibol. And it's a weird thing to pronounce because I've seen it used like this. And then, I don't think that's like a hydride, that's not reversible. And then you end up with this hydrogen on something else, and you have, but like, how do I pronounce Dibol with a negative charge different from Dibol? Like, do I just breathe aggressively at the end for that? I don't know. So I'm gonna call them both Dibol, and we don't care. What we do know is that Dibol is a specifically made reducing agent that is going to be able to reduce an ester to an aldehyde. And I say aldehyde specifically, not ketone or aldehyde, because usually, like, I don't know, it's either a ketone or aldehyde. It depends on what's bonded to it, right? But an ester always has, that's a double bond, this nice little leaving group, right? So an ester is only ever going to have one R group on it to begin with, or the carbonyl carbon. The carbonyl carbon of an ester is only ever going to have one R group on it to begin with, right? Because the other R group is attached to an oxygen over here, and that's a really nice leaving group. So when we do this like partial reduction or the one-step reduction using Diol, we always end up with an aldehyde. So Diol reactions. We put a bunch of stuff around this. If you noticed, Diol is an alcohol, so it's aluminum. God, it's like the metals don't exist at all. They just, I don't know, I purposefully forgot them. So it's also an aluminum thing, like LAH, but instead of the really aggressive LAH, we've got some big, more stabilizing groups on there. So, in order to actually get the desired reaction, like the whole reason you would use Diol, you're going to be doing this reaction at negative 78 Celsius. So again, acetone and dry ice bath, which is not something that you touch the glassware with just wearing nitrile gloves, because you will definitely start to lose, like, I'm talking lose feelings in your fingertips for like a couple days. Like, I don't know if that's technically frostbite, but like, it's not fun. It's not negative 8, oh. Okay, yeah, I guess. Negative 78 is really close to negative 80. I don't know, I just always compare things to negative 80 because the negative 80 freezers exist and all the biochem people use them, and you kind of have to really not care about your nerve endings to just not use the gloves. Like, you really should be using the gloves to touch things in the negative 80 freezer, and yeah, well, I probably should have looked up the temperature before I started just playing with that. But we cooled this down a whole lot, and we're actually going to be able to stop that halfway. So these halfway guys, both the reduction halfway to an aldehyde or the substitution, substitution reduction, I mean it's both of them,